Okay, now let us try to discuss, or let us discuss the part of the bandgap voltage reference design, which is the CTAT. So we will be discussing the complementary to absolute temperature circuit. So this complementary to absolute temperature circuit, so let us consider here a constant current that is flowing through the diode that is constant with respect to temperature and supply. So across the diode here is the voltage, the VD, which is the voltage of the diode. And we all know that the current flowing through the diode is just the same here, follows this formula, which is IO is equal to IS e raised to VD over VT, where VD is the thermal voltage, which is equal to 26 millivolts per 300 Kelvin. And we know that here the voltage VD is the voltage across the diode, and IS is the reverse saturation current of the diode. And we can get the value, simplifying this equation here, we can get the ratio of the current over the saturation current and solve for the voltage of the diode. So here we just transpose the values of IO over IS. What we have left is e raised to VD and VT. So in order to solve for the diode of the voltage, or the VD, we can apply natural logarithm, multiply both sides by ln, and simplifying that, we can get VD is equal to VT ln IO over IS. So with that, this voltage here is CTAT in nature. So since this is ln I over IS, we can graph it this way. So the voltage across the diode here is CTAT in nature. And the question is, what is the slope of this voltage that is changing, or how quickly it is changing with respect to temperature? So based on industry standard, or of what you can see in the book, but it is around negative 1.6 millivolts per degree Celsius. But this value of negative 1.6 millivolts per degree Celsius is not fixed. But if you will calculate it, or in qualitative analysis, if you calculate it dili lang yun sa kanang simulation, you can use this value of negative 1.6 millivolts per degree Celsius. So, ano siya. As a continuation, we will try to discuss the relationship of the diode voltage with respect to temperature. And from our derivation from our previous slide, we know that the diode voltage is equal to the thermal voltage times the natural logarithm of IO over the IS, or the reverse saturation current. And take note that the IO, I sub O, is a fixed current. It is assumed a fixed current that is not changing with temperature and input supply. And with that, we also discuss, and we also show that the diode voltage with respect to temperature, it is the standard value according to the textbook is equal to negative 1.6 millivolts per degree Celsius. And we all know that it is not fixed, but it can vary from time to time. So it is just the for analysis, qualitative analysis. And with that, it can be said that the diode voltage is zeta in nature because of this negative time. It has a slope of negative, and the diode voltage is decreasing with respect to temperature. So how does it goes like that? So we will discuss that first. So from this, as you can see, we know that a diode voltage has two terms. It has, I'm sorry, my mouse is not working again. So the diode voltage has two terms. It has the thermal voltage and the natural logarithm of the I0 over Is. So, and also, as discussed earlier, the thermal voltage is equal to the Boltzmann constant times T over Q, the carrier, wherein we can see it is explicitly shown that the thermal voltage is proportional to this temperature here. And as I have said earlier, when the voltage or the current is proportional to temperature, then it is a pitat. So this Vt here is a pitat. But how can we say that this diode voltage is a cetat? So, as we all know, this term, automatically, this term of natural logarithm of I over Is is a cetat. And how does it become cetat? We will discuss it elaborately later. So, we further discuss ang Vt for the change of Vt over T, kung partial derivative nato, the value of the change of voltage with respect to time is equal to Kq. So this is an important equation here, which is also same with this very important equation that we will use later on. So we're done with the relationship of Vt, or the thermal voltage, with respect to temperature. Now, let's deal with the second term, the ln over I0 over ln I0 over Is. So, again, I0 is a constant with respect to temperature. So, when it is constant, the derivative of I0 with respect to time is equal to 0. So, any constant value, derivative of that is equal to 0. So, we assume that Is is the culprit here, where it gives the big influence, or it has predominantly dictate what the Vd is, which is in cetat. So, we know that Is is the reverse saturation current of the diode. So it has intrinsic property of the diode, but it depends very much of the temperature and the process. So with that, we will discuss elaborately the terms that this reverse saturation current depends on, para makita nato unsay nahitabo nganong nasitat ang atong diode voltage. As we have said that the I0 is a fixed current, and it does not vary with the derivative of I0 is constant, which is equal to 0. So ln of I0 over Is, ang dependent sa temperature, wala nagdependent sa I0. So, the second term that is in the ln I0 is the Is. So, by device physics, so dili na ni siya appeal sa analog circuitry, but with this equation here, we can inspect it so that we can get the relationship of Is with respect to temperature. And just recall that mu, just recall your device physics, that mu is the mobility, and K is the Boltzmann's constant, and T is the temperature, and Ni is the intrinsic carrier concentration. And with that, our mobility or the mu is proportional to the mu sub o times t raised to the power of m, where m is equal to negative 3/2. And next is our K constant, and T the absolute temperature, and Ni, which is proportional to T to the 3 e raised to negative Eg kT. So Is, with this property or with this values that we have from these terms, which is terms inside our Is, we can say that we can write our Is in this term by letting mu sub o k is equal to b para maisa nato ang constant kay since ang mu sub o ug ang k is our constant, then we can compress it into one term which is equal to b. Then we can write Is is proportional to b times dt, since kini mu sub o times t, so as is ang t, then t sub m, then Ni t sub 3 t to the power of 3 e raised to the power of negative Ej kT. And with that, we can say that this will be our reverse saturation current. And by adding the terms by law of exponent, we can say that Is is proportional to b times t raised to the power of 4 plus m e raised to negative Eg kT. So we can simplify this term. Since kay proportional naman siya sa constant, then we can say that Is equal to b times t raised to the power 4 plus m e raised to negative Eg kT. And we can save this term as equation 3. Save it for later for kato sa mga equation that we will deriving. And our concern is to get the relationship of Is with respect to sa temperature. So we have the partial derivative of Is with respect to temperature, and we can get that by differentiating the Is with respect to time by getting the first term times the differential of the second term plus the second term times differential of the first term. So balik ta sa atong differential equation, no? So kini ang atong gipagawas nato ang b, kay naman tayo duha ka terms, t raised to the 4 plus m ang first term, and the second term ani e raised to negative Eg kT. So the first term times the derivative of the second term ani e raised to negative Eg kT times negative Eg k times negative 1t squared. Next is add the second term plus times the derivative of the first term. So we have e raised to negative Eg over kT times 4 plus m times t raised to the power of 3 plus m. So as you can see, we have common terms here. Ang e raised to negative Eg kT. So we can put that outside. So we have here b e raised to negative Eg kT times t raised to 4 plus m times Eg kT squared plus 4 plus m t raised to the power of 3 plus m. And another common term that we can put outside is t 4 plus m. So dili man siya explicitly nga same, but we can make it nga mapareho sila. So we have put that outside, t raised to the 4 plus m b times t raised to the 4 plus m times e negative Eg kT squared. So we have, what we have left is Eg kT squared plus 4 plus m t raised to negative 1. Diba? Kung mag plus 1 tama 4 na na. So we have this. Ma-equate lang gihapon na to ang term. So, as you can observe, kini nga term, the b times t raised to 4 plus m, e raised to negative ag kt, which is this, is just the is value. So, with that, let's substitute it again. So, we have the is, partial derivative of is with respect to temperature is equal to is eg over kt squared plus 4 plus m over t. Then rearranging it for simpler terms, so we have partial derivative of is with respect to temperature is equal to is times 4 plus m over t plus eg kt. Wala na yung plus, sorry. So, ano. So, next, let us fuse the terms of katong para makuha nato ang relationship sa diode voltage with respect to temperature, since we all get the nakuha na nato ang partial derivative of Vt with respect to time, and also we also get the second term na relationship, partial derivative of Is with respect to temperature. Already have derived the value of we already get the value of the temperature voltage, and also the partial derivative of the temperature voltage, and also the relationship or the derivative of Is with respect to temperature. Now we can get the the relationship of the voltage with respect to temperature, the change of the diode voltage with respect to temperature. Since we already know that, as by equation, we know that Vt and Is is dependent with temperature. So basically, these two terms play a vital role in the characteristic of the diode voltage. So we can get the partial derivative of the diode, or the change of the diode voltage with respect to temperature, by the partial derivative of the first term times the second term plus the second term times the partial derivative of the second term. So using that equation, we can get, so as is lang sa nato, then first let us derive this first, because the independent value with respect to temperature of this term has in its inside of the ln, which is is. So we have the partial derivative of ln io over is with respect to temperature is equal to 1 over io over is times the negative io over is squared times the partial derivative of is with respect to temperature. So simplifying it, canceling the like terms, so we have the partial derivative of the diode voltage with respect to temperature is equal to partial derivative of Vt with respect to temperature times ln io is, ln times io over is, minus Vt times 1 over is naman lang nabilin dire, times partial derivative of is with respect to temperature. And we know that we already derived this partial derivative of the temperature voltage with respect to temperature, which is in equation 2, and the partial derivative of is with respect to temperature is derived in equation 4. So substituting those values into this equation, we know that a partial derivative of Vt, just recall that partial derivative of Vt with respect to temperature is equal to Kq. So we have Kq times ln io over is minus Vt times 1 over is times, we know that the equation 4 is equal to is times 4 plus m over t plus eg kt squared. So with that, cancel the like terms, so we can simplify. Then simplifying it, so we have, we know also that Vt is equal to KTQ, right? So K over Q is just equal to Vt over T. So we have Vt over T times ln IOIS minus Vt over T times 4 plus m minus Vt Ag Kt squared. So with that, we can simplify with that value. We know that Vt is equal to KTQ. So in order to cancel this, so we have same terms and we know that kining Vt times ln IOIS is just equal to the diode voltage. So we have the partial derivative of the diode voltage over temperature is equal to Vd over T minus Vt over T times 4 plus m minus KTQ Ag Kt squared. So kini po gipulihan nato Kt over Q para makancel ang temperature kana wag ang K. So with that, so we have partial derivative of the diode voltage with respect to temperature is equal to Vd over T minus Vt over T times 4 plus m minus Ag Qt. So observe that the common term is the temperature, so we can put the temperature outside, the term T outside. So we have, or sa denominator di, so we have Vd minus 4 plus m minus Ag Q. This is Q. Sorry, I am mistaken. So Ag over Q ni siya. So all over temperature. So basically, naatay mga ideal value for Vd and Ag over Q, which is the bandgap ng Ag nga value. And Vd is the diode voltage ideal value. So we can get the change of the diode voltage with respect to temperature by substituting those values. So we know that basically sa mga ideal voltages for diode, so we have 0.7. So minus 4 minus ang katong m, as I have mentioned, for the mobility, we have m is equal to negative 3 halves. Okay, nakalimtan ang Vt diri nga term. So kana Vt. So Vt is equal to 26 millivolts minus 1 half. So all over 300 at 300 Kelvin. So substituting those values, we can get a negative 1.88 millivolts per Kelvin. So much closer with negative 1.66 millivolts per Kelvin sa katong gipakita as we have shown earlier. So basically this slope or the change of the diode voltage with respect to temperature varies accordingly because this diode voltage is not absolute, mag-change po din siya. It can vary from 0.6 to 0.7 to 0.8 rather. And also this bandgap voltage can be of the value of 1.1, 1.2 and so on. So it could be a factor that change this slope here. So that's it. So we just derived, we have just shown how is the diode voltage with respect to temperature relates kanang what is the relationship between the two, or the slope of the diode voltage with respect to temperature. So next topic, we will try to simulate the CTAT circuit so that we can show you how is CTAT is done. So see you.